Section 10.7 Text Compression. Section 4.2.1 discusses the use of Huffman codes for compressing text. Several strong encryption schemes can be based on text compression. In this section, I present several more advanced text compression schemes and some encryption schemes based on Huffman codes. The remainder of Chapter 10 is optional. If at any point the math becomes too daunting, just skip directly to the next chapter. Section 10.7.1 Lempel-Ziv. The Lempel-Ziv text compression scheme was developed by Israeli computer scientists Abraham Lempel and Yaakov Ziv in 1977, called LZ77, with an improved version in 1978 called LZ78. It is based on the same underlying concept as Huffman encoding, namely letters and letter combinations are represented by binary codes, that is, by groups of bits. However, Lempel-Ziv takes the opposite approach to this. Huffman uses shorter codes in order to save space. Lempel-Ziv uses codes of roughly the same length, but has some of the codes represent longer letter combinations to save space. Huffman and Lempel-Ziv are opposite in another sense too. Huffman bases the length of the codes on a fixed preset table of letter frequencies. Lempel-Ziv determines the most frequent letter combinations on the fly while it is encoding the text. This is known as adaptive coding. Huffman encoding is good only for text in a single language. A different language would have different letter frequencies. Even changing from uppercase to mixed-case text would require a different set of Huffman codes. By contrast, Lempel-Ziv can be used for any type of computer file, text in any language or mixed languages, computer code, images, telemetry, music videos, and so forth. There are several versions of Lempel-Ziv. The version I present here, called Lempel-Ziv Welsh, or LZW, was developed by Terry Welsh of Sperry Research in 1984. LZW has both fixed width and variable width versions. I am presenting the variable width version, which is easy to adapt for cryptographic use. All versions of Lempel-Ziv use a list of letters and letter combinations, called a dictionary. The dictionary is built on the fly as the algorithm progresses through the file. In the LZ77 and LZ78 versions, the dictionary starts empty. The code for any given letter combination is its location in the dictionary. LZW begins by assigning a code to each of the single characters in the file. LZW codes all have the same number of bits. For example, if the file were a message in English, all in uppercase without punctuation or word divisions, then you would need 26 codes, so you could use 5-bit codes. It is more common to start with 256 codes, one for each of the 256 possible values of an 8-bit byte. As the algorithm progresses through the file, it looks for letter combinations that are not already in the dictionary. When it finds one, it adds that combination to the dictionary. For example, suppose that the algorithm has found THE in the file, and that THE is already in the dictionary. Suppose the next letter in the file is M, and that THEM is not in the dictionary. It outputs the code for THE followed by the code for M, and adds THEM to the dictionary. The code for THEM is the next available location in the dictionary, say 248. Since THE was already in the dictionary, the algorithm will not look at combinations starting with HE or E. It will start at M, looking for another combination that is not in the dictionary. If that combination is MOR, then MOR is put in dictionary entry 249 and has the code 249. The next time the algorithm finds THEM in the file, it will be coded as 248, and the next occurrence of MOR will be coded as 249. When the algorithm has filled up all 256 dictionary entries for 8-bit codes, the next assigned code will need to have 9 bits. At that point, the algorithm will switch from 8-bit codes to 9-bit codes. THEM will still have the code 248, but it will be the 9-bit code 011111000 instead of the 8-bit code 11111000. When the algorithm fills up all 512 dictionary slots for the 9-bit codes, the code for THEM becomes the 10-bit code 0011111000, which is still 248. Note the order of these operations. The code for the current letter combination is output first at the old size, then the new combination is added to the dictionary and the code size is increased. Both Sandra and Riva must use the same order, or else the message will not be decompressed correctly. Enlarging the codes typically stops at 12 bits. Increasing the code size from 12 bits to 13 bits usually does not improve the compression and may even worsen it. Let's look at an example. Let's encode the word tête-à-tête using this algorithm. Suppose the dictionary starts off with the single letters A, E and T using 2-bit codes. Let's follow the dictionary as it gets built. At each stage, the bit strings to the left show the encoded word, while the letters to the right show the remaining portion of the word. When Riva decompresses the message, the dictionary must be built up exactly the same way. Note that the bit string 100101000011 by itself is not enough for Riva to decompress the message. She also needs to know that the codes 00, 01 and 10 represent the characters A, E and T. Okay, that's Lempel-Ziv compression. This is a book about cryptography. How can Lempel-Ziv compression be used for encryption? In building the dictionary, Lempel-Ziv assigns codes sequentially. The 43rd letter or letter combination will get the code 42, not 43 since the codes start at 0. To use this scheme for encryption, add a second column to the dictionary. The first column contains the letter combinations and the second column contains the corresponding codes. Instead of using the position in the dictionary as the code for each letter combination, use the number in the second column of the dictionary. Suppose that the dictionary starts with the 256 single-byte characters. The first column will contain the characters. In the second column, put the numbers from 0 to 255 in some scrambled order. They can be mixed by any of the methods described in section 5.2. Sandra and Riva must use the same order, which could be determined by a keyword or by the seed for a random number generator. When the first 9-bit code is needed, the next 256 dictionary entries will get the codes from 256 to 511 in scrambled order. Likewise, when you move from 9-bit codes to 10-bit codes, the next 512 codes will be assigned at one time. Assigning codes in bulk is more efficient than assigning them one at a time. An alternative to assigning the codes in bulk is to assign only the first 256 codes, using a keyword or random number sequence. After that, each new code is calculated by adding 256 to the code 256 entries earlier. That is, x of n equals x of n minus 256 plus 256. This cipher, which I will call Lempel-Ziv substitution, is rated 3. The rating is so low because the first few characters of the message are essentially enciphered with simple substitution. Each code will represent a single character until the first repeated bigram occurs. This might not happen until 30, 40 or more characters have been encoded. Even after that point, most of the 9-bit codes will represent single letters. These codes are easily distinguished because they are the only 9-bit codes starting with 0. Emily will have plenty of opportunities to use both letter frequencies and contact frequencies to crack the message. To make Lempel-Ziv substitution strong, you can add a second substitution step. This substitution should not be on byte boundaries. I suggest using 7-bit groups. These groups will not coincide with the code groups until the codes reach 14 bits. This may never happen because codes are usually limited to 12 bits. Lempel-Ziv substitution followed by a 7-bit substitution is rated 6. Both substitutions can be accomplished in a single left-to-right pass.